Okay, I think we are live. Finally, after 10 days of being in China, we are kicking off the streaming again. Let me just share the streaming link. We're back. We're so back. Just remove the embed here. And I'm gonna dig right into the work. Guys, I'm planning to, over the next 90 days, have zero break. I'm planning on working every single day over the next period. So I really want to push this project forward. So super excited. Hi, Vivek. Nice to see you, man. Welcome back. Let's go. We stopped the last time we were at the locality sensitive hashing block. We were just getting some familiarity with how this works, and I think I grokked it the last time, but because of the last 10 days I was in China and I was not working on the project, I need a bit of to do some context switching, so it would be good to go through the blog again. And then the plan for today is to basically start pushing the HBS data, so that means Serbian, Croatian, Bosnian, through the preparation and filtering pipeline, so we can kick off the first run for the 650 million model. That's the idea. I want to see whether, I think we will need the locality sensitive hashing as a part of our fuzzy deduplication. So because of that, I want to quickly go through this block. Let's kind of skim through it again. Okay, I don't think we need to focus on the details here. I just want to see how exactly it works. Search complexity, we don't care about that. Okay. This is just still high level stuff. Okay, here is the actual explanation. So, the LSH approach we're exploring consists of three-step process. First, we convert text to sparse vectors using k-shingling and one-hot encoding. Then we use min hashing to create signatures, which are passed onto our LSH process to weed out the candidate pairs. Okay, so the shingling here is like just grabbing the 2 grams from your input sentence, and then you get a representation here. You convert that into the sparse vector, and then using the multiple permutations, we end up with a code. So that's the part I'll need a bit of refreshing how exactly this works. I kind of forgot some of the details. And ultimately we end up with a representation that's much lower dimensional than the original sparse vector. And then we can use that representation to basically find for similar input sequences. I do fuzzy duplication. That's the idea. So let's go through the process. K-shingling, or simply shingling, is the process of converting a string of text into a set of shingles. The process is similar to moving a window of length k down our string of text and taking a picture at each step. We collate all of those pictures to create our set of shingles. Stress on the set here, it's not a list. So we just need unique elements. Okay, and then shingling also removes duplicate, hence the word set. We can create a simple k-shingling function in Python like so. Okay, we're just appending and we retrieve back the set. Okay, that makes sense. And with this, we have our shingles. Next, we create our sparse vectors. To do this, we first need to union all of our sets to create one big set containing all of the shingles across all of our sets. We call this the vocab. Okay, and then we use this vocab to create a sparse vector representation. All we do is create an empty vector full of zeros and the same length of it as the vocab, and then we look at which shingles appear in our set. Okay, so for a particular representation for this sentence, we see which of the shingles we've got, and that's how we form the representation. All of that makes sense. Let me just see quickly the code. Just open up VS Code. Do you guys hear me well, by the way? Let me know if there are any issues with the sound. Hopefully you can hear me well. Okay. This was the function, this was the script we had the last time. This was just a demo for using the min hash from this data sketch package. And so what we do, we basically want to understand exactly what all of these parameters mean. So we open up the lines, we strip the lines, we create a min hash, we update the min hash, and then we insert that min hash into here. And this is going to build up the vocab inside of the LSH object. And then when we query, okay, just trying to connect the code with the blog. And so for every shingle that appears, we identify the position and set respective position to 1. This is the one hot encoding, and then min hashing. In the next step of the process, allowing us to convert our sparse into dense. Can seem confusing initially, but it's very simple once you get it. I agree. So we have our sparse vectors, and what we do is randomly generate one min hash function for every position in our signature. Okay, so we generate one min hash function for every position in our signature. So that depends on the dimensionality of the dense vector, basically. So if we wanted to create a dense vector of 20 numbers, we would need 20 min hash functions, which are basically just random permutations, as we'll soon see. So now those min hash functions are simply a randomized order of numbers, and we count from 1 to the final number. Because the order of these numbers has been randomized, we may find the number 1 is in position 57, for example, of our randomized min hash function. Okay. Our signature values are created by first taking a random permuted count vector and finds the minimum number that aligns with a 1 in our sparse vector. Hey Smith, welcome man. Nice to see you here. Okay, let me just recall what exactly we do here. So we shuffle, and we ask whether, okay, 1, 2, okay, got it. So we look at the first number that aligns with 1 in the permutation. So here in this example, 1 doesn't align with 1, 2 aligns with 1, that's why we grab 2. That's how we build a single dimension of the output dense vector. This will make sense more in a second if you haven't seen this before. If you want, you can check out the last video. We went through this and we grokked it on the video before my China trip. So our signature values are created by first taking random per vector and finds the minimum number that aligns. Yeah, okay. So above we are using a small vocab containing 6 values so we can easily visualize the process. We'll look at our sparse vector and say, did this shingle at vocab 1 exist in our set? If it did, the sparse, just a second, that vocab 1 exists in our set. If it did, the sparse vector value will be 1. In this case, it did not exist, hence the 0 value. So we move the number to number 2, identify its position, and ask the same question. This time the answer is yes, and so our min hash output is 2. That's how we produce one value. But we need to produce 20 or more of these values, so we assign a different min hash function to each signature position and repeat the process. So again, here we start with 1. You can see here we have 0, so we don't use this one. So we go to 2. 2 is aligned with 1, so that means we put 2 here. Here we have 1, which is 0, so we ignore it. 2 is 0, we ignore it. 3 is 0, we ignore it. 4 is the first element that is aligned with 1. That's why we put 4 for this particular permutation. One of your colleagues deleted the production Elasticsearch. Okay, man. Take care. Crazy stuff. Okay, here 1 is immediately aligned with 1 in our sparse vector, so we just add 1. And here 1 is not, but 2 is aligned with the vector. So that's how we end up with the signature 2, 4, 1, 2 for this sparse vector for these set of min hash functions, which are basically just permutations, random permutations of our vocab indices starting with 1. So 1 indexed array is just being permuted. Okay, makes sense. The only part that was confusing is what does vocab of 1 mean? Does it exist in our set? Vocab of 1. This is kind of confusing notation. I know what they mean. So does this shingle exist? Because it does not exist. Okay. Anyhow, let's go to the code. Generate a randomized min hash vector. So we just do a range list and then we do shuffle, and that's the first vector. And then loop through this randomized vector and match the index of each value to the equivalent values in sparse vector. Index of 7 can be found at index 1 in the hash. Okay, what we do with this is count up from 1 to length plus 1 and find if the resultant hash contains a positive value in that position, like so. We go through the vocab, we ask for the index, and we see whether this is 1. If it is, it's a match. Okay, so that means 6 is the first element of our signature. Okay. So build a signature for multiple iterations of 1 and 2. We'll formalize the code from above into a few functions easier to understand. Let's see this one. So again, we create a hash function. We add a bunch of these hash functions to the min hash. So we have like 20 min hash vectors. And then to create a hash, we go through the hash functions and we just repeat the process above. We try and find the first index, the lowest index where the vector of that index equals 1. Okay, so vector of that index equals 1. So we first ask, where is 1? What's the index of 1 in the min hash function? We get its index, and then we ask, hey, is this aligned with 1 in the sparse vector? And that's how we end up with the signature. I understand mechanistically what's going on. I'm not sure the underlying theory. Why does this work? That's I guess a bit deeper than what this blog can offer us. Although it doesn't matter for the purpose of why I'm doing this is just to get a basic understanding how I can use this. Okay, and that's min hashing. Nothing more complex than that. We've taken a sparse vector and compressed it into a more densely packed 20 number signature. Okay. So now the part that I'm interested in is how do we do the bucketing. This is the second part that's important. The final step is in identifying similar sentences is the LSH function itself. We'll be taking the banding approach to LSH, which we could describe as the traditional method. It will be taking our signatures, hashing segments of each signature, and looking for hash collisions, as we described earlier in the article. Okay. So we are hashing the segments of each signature and looking for hash collisions. So we do the shingling, we get the sparse, we get the signature. And through this method, we produce these vectors of equal length that contain positive integer values in the range 1 through length of the vocab. And that's the input for the LSH. Okay. Now, if we were to hash each of these vectors as a whole, we may struggle to build a hashing function that accurately identifies similarity between them. We don't require that the full vector is equal, only the parts of it are similar. In most cases, even though parts of two vectors may match perfectly, if the remainder of the vector are not equal, the function will likely hash them into separate buckets. We don't want this. We want signatures that share even some similarity to be hashed into the same bucket, thus being identified as candidate pairs. Okay, so how does this work? The banding method solves this problem by splitting our vectors into subparts called bands B. Then, rather than processing the full vector through our hash function, we pass each band of our vector through a hash function. Okay. So imagine we split a 100-dimensional vector into 20 bands. That gives us 20 opportunities to identify matching subvectors between our vectors. So here we have 3 is the size of the signature, and we have 3 bands. In this particular example, well, actually 3 times r, whatever r is. I think this is the notation that our package is using as well. So here, this package called data sketch, if we take a look at min hash LSH, and if we take a look at the actual notation here, we have LSHB and LSHR. So it seems that's kind of traditional notation for this algorithm. Okay, and so we end up with subvectors, and then we map those using hash functions into the buckets. And if there is a if some other vector basically maps into the same bucket, into the same slot inside of this hash bucket, that means they're similar, and thus we infer that the whole input vectors are similar, thus the input sentences are going to be similar. Okay, we can now add a more flexible condition. Given a collision between any 2 subvectors, we consider the respective full vectors as candidate pairs. So you can see here, these 2 are not the same. We have vector A and B. These do not collide, but in the 3rd band, they collide. And then we say, hey, these are the matches. Okay. Fairly simple process. Of course, you can always dig into deeper mathematics to understand exactly how this works. But for the sake of what I'm trying to do, I don't care. Okay, now only part of the 2 vectors must match for us to consider them. Only one part needs to be matched. But of course, this also increases the number of false positives, samples that we mark as candidate matches where they are not similar. However, we do try to minimize these as far as possible. Okay, so we can implement a simple version of this. First, we start by splitting our signature vector A and B and C. So we split them into subvectors using basically all of the subvectors are going to be of dimensionality r. So we split into 10, and it has to be divisible by 10, obviously. That's how we get the R. Okay, this is just how we split into the subbands. And then we'll loop through the list to identify any matches. So we'll loop through those. If they're the same. Okay, this is incorrect because we don't want to compare the subbands directly. We want to compare the index that was given to us by the hashing function. So this is, I think, incorrect because they go through the signature. So A sig and B sig were just computed up above. Let me just see quickly. Yes, so we have the A sig and B sig, which are basically 20-dimensional vectors. In this particular example, 20, 5, 15, 20. So what they've done here is, I think, a mistake. Oops, let me quickly see. Where did we stop here? Okay, here. This is incorrect. You can't go through the bands and compare them directly. Okay, testing LSH. What we have built thus far is a very inefficient implementation. If you want to implement LSH, this is certainly not the way to do it. Rather, use a library built for similarity search like FICE or a managed solution like Pinecone. Okay, well, we got the gist of how it works on the high level. Okay, so here they just have some example. They fetch some data. They have some sentences here. Hi Navjot, hey man, welcome back to the stream. We are back. Okay, this is just some NLI task. We don't care about this. So we first create the shingles. We go through the sentences and we create 8 n-gram shingles. Then we build the vocab. Then we convert the shingle set into the 1-hot representations. Okay. We have 4,500 sparse vectors where each vector is of length 36,000 because that's the size of the vocab. And then we do the min hashing. We grab the signatures. Okay. And then we've compressed our sparse vectors from a length of 36,000 to 100. And finally, we call the LSH. The full code can be found here. We're going to check it out in a second. So we use the band, so 20 bands. That means that basically we'll be comparing only 2 numbers for collision. Because our original vector has like 100, which means r equals actually 5, sorry. Because we have 20 bands, each of them is going to be 5 dimensions in length. And then we call add cache on the signature, and then we end up with buckets. It's important to note that our LSH buckets variable contains a separate dictionary for each band. We do not mix buckets between different bands. We see in our buckets the vector IDs. So all we need to do is extract our candidate pairs, is loop through all the buckets and extract the pairs. After identifying the candidate pairs, we would restrict our similarity calculations to those pairs only. We will find that some will be within our similarity threshold and others will not. The objective here is to restrict our scope and reduce search complexity while still maintaining high accuracy in identifying pairs. We can visualize our performance here by measuring the candidate pair classification against actual cosine similarity. Okay, let's quickly, before we go there, let's just check out the implementation here. Too big to display. What? Do I need to really download this? Let's quickly download this piece of code. if GitHub allows me. Okay, testing, let's just go to the home, projects, NLLB. Let me put it somewhere in the root of fairsec or something. Maybe here, testing LSH. I'll just cancel. Okay, we are back in fairsec. Testing LSH, let's find this file. Testing LSH. Here it is. Okay, we've seen this code before. Okay, here's the implementation of the LSH here. Let's see how it works. So we keep on adding the hashes, which are going to be the signature. So let's see how it works. So we have buckets, counter. We store the number of bands. And for each of the bands, we store a set. Or a dictionary, I guess, here. And then when we call add hash, we pass signature to make subvectors, which basically gives us back chunked signature into B bands. So we end up with the subvectors. And then what do we do here? We go through those subvectors. We convert them into strings, apparently. And if it's not already in the bucket, just a second, if it's not already among the keys, in that case, we first initialize with the empty list, otherwise we append the counter. Okay, so for this bucket and this subvector, we append the counter, which basically tells us that's the idea of the signature. So that means, okay, this is definitely some dummy implementation because they're not actually using hash functions. They're just, or actually they are, because underneath they're using dictionary, which is using hashing. Let me just think for a second. So for band I, of which we're going to have 20, so 0 through 19 is where index I goes through. And then for each of those bands, we keep subvectors we've seen before. And sometimes for multiple signature, that ith band will be the same. And so we want to basically just make sure that we remember which signatures, i.e. which input sentences had overlaps. So we'll ultimately end up having candidate pairs collected inside of the bucket. And then when we call the check candidates, we go through the buckets, we grab the keys, and then if the length is bigger than 1, that means that we have some candidates. Okay, and then we do what? We extend the candidates list with combinations. What's combinations? Combinations of hits 2. What is going to be the output of this one? Let me think for a second what makes sense. What makes sense here is So imagine we have like 3 different input signatures where are potentially candidate pairs. So that means we might have something like a list of 1, 13, 20 instead of hits. We pass it into combinations. It might give us like 1, 13 and 13, 20 and 120 as the 3 potential combinations, meaning those are duplicates. But why would we want to do that? Let me just see quickly. So iter tools, combinations. Let me quickly see what they say about the function. Returns the R-length subsequences of elements from the input iterable. Okay, got it. So as an example, if we give it A, B, C, D, and 2, it's going to give us all 6 combinations there. Okay, that's what I expected. And okay, we end up with buckets. And you can see here, all of these are 5 in length, as expected, because we have original input is 100, we have 20 bands, and each of the subvectors is going to be of 5 dimensions. So this means basically these 2 examples are duplicates, because for this particular band, they overlap. So all we need to now do is call the check candidates and then see how many duplicates we have. That's how many pairs we have. Will this be unique? Okay, not sure about the uniqueness, but this now makes sense. Let's go back to the blog. Just a second, where did I store it? Okay, let's go back to the blog. Check the candidates and we list all of them here. Okay, and then they say, let's see these visualizations. After identifying the candidate pairs, we will restrict our similarity calculations to those pairs only. We will find that some will be within our similarity thresholds and others will not. The objective here is to restrict our scope and reduce search complexity while still maintaining high accuracy in identifying the pairs. Okay. Okay, let me just think for a second. What do we see here? So candidates is probably what... Okay, candidates is what the output here gives us. And then we also plot their actual similarity. But do we do the similarity? I guess we do similarity across their signatures. And we can see that sometimes it's definitely not a perfect classifier, because sometimes we have super high similarity and the LSH tells us they are not candidates. Okay, optimizing the bands. It is possible to optimize our band value to shift the similarity threshold of our LSH function. The similarity threshold is the point at which we would like our LSH function to switch from a non-candidate to a candidate pair. We formalize this probability similarity relationship as so. Probability of a pair being identified as candidate pair given a similarity score S, number of bands P, and number of rows in each band R. Okay. Where do we specify S in the actual algorithm? Now, if we were to visualize this probability similarity relationship for our current B and R values, we should notice a pattern. Okay, let's see what's up here. I'm still not sure what S, how S is specified. Is it implicitly specified or what? Candidate classification left y-axis and calculate probability right y-axis against similarity. Calculate or normalize cosine. Aha, that's the cosine similarity. Okay. This shows that our calculated probability P and similarity S values indicate the general distribution of candidate non-candidate pairs. The B and R values are 20 and 5 respectively. Okay, got it. So basically by specifying R and B, we are creating a certain distribution like this one here. I mean, not distribution, this is just, I guess CDF. And then we can manipulate these two to get a different type of a chart. We can see a correlation between the theoretical calculated probability and the genuine candidate pair results. Now we can push the probability of returning candidate pairs at different similarity scores left or right by modifying B. As you can see here, if B is too high, then we start saying that the vectors are duplicates very soon. Even when there is like a very small similarity, we immediately label those vectors as the same ones, as fuzzy matches, just because we only have 2 dimensions across which we compare, and then that means it's easier to have a collision. For 5, on the other part of the spectrum, because now our subvectors are of 20 dimensions, it's harder to find a collision, and because of that, only for very, very high similarity scores do we actually output 1. Okay. So these are our calculated probability values. If we decide that our previous results where B required too high a similarity to count pairs as candidate pairs, we would attempt to shift the thresholds to the left. So shift to the left to reduce the similarity for which we say that they are candidates. So looking at this graph, a B value of 25 looks like it could shift our genuine results just enough. So let's visualize our results when using B25. And this was for B20, I guess. Yes. Okay, so let's see. Note that this has created more candidate pairs. Because we're now returning more candidate pairs, this will naturally result in more false positives, where we return candidate pair for the similar vectors. this is an unavoidable consequence of modifying B. So we have more, because when we use 20, wait just a second. So when we have red is 25, that means we end up with only 4 dimensions per subvector, which means higher likelihood of collision, which means more pairs are going to be labeled as duplicates. Okay. And which we can visualize like this. Increasing B, shifting left, increases false positives while decreasing false negatives. Okay. Makes sense. So we built the LSH process from scratch and even managed to tune our similarity threshold. That's everything for this article on the principles of LSH. Not only have we covered LSH, but also shingling and min hash function. We'll be covering LSH, specifically the random projection method, in much more detail alongside its implementation in PICE. Let's see what's this overview of the indices, choosing the right index. Okay, this is kind of the deep theory behind vector databases. We can maybe quickly skim through this just to extract the parts that are necessary for us. Yeah, let's go through that block. Let's see what's interesting here. Choosing the right index. Okay, there is no one size fits all. This great flexibility produces a question: how do we know which size fits our use case? Which index do we choose? Flat LSH HNSW blah blah blah. Okay, we already know we want to use LSH. HNSW, I think this stands for like hierarchical something small world index. This is something that like VV8 uses, I think, maybe even Pinecone. Let's just kind of skim through all of this. Flat and accurate. When to use, implementing it, balancing the search time, LSH. Let's see what they say about LSH, because that's the one we know we want to use. Hierarchical navigable small world graphs. Okay, that's what the acronym stands for. Navigable. Quality, speed, memory. Poor performance for high dimensional data. Grouping into buckets by processing each vector through a hash function that maximizes hashing collisions, rather than minimizing as is usual with hashing functions. Okay, we've seen this already. A Python dictionary is an example of a hash table. using a typical hashing function that minimizes the collisions. Okay, we've seen all of this. Higher value of n bits results in greater accuracy at the cost of more memory and slower search speeds. Recall the score of index LSH with dimension of 128. Note that to get higher recall performance, we need to increase the number of bits dramatically. For 90% recall, we would use 64 dimensions. So 64 and 128 bands or what? I'm not sure what this is saying. Our baseline. We can achieve 90% using a very high m bits value. Let me just think for a second. What are they saying here? Okay, so out of 100% exact candidates, we can fetch 90% of them. And in return, we get much faster search times. That's the inherent trade-off of using something like LSH. Highly sensitive to the curse of dimensionality. When using a larger d value, we also need to increase the n bits. They're using a bit different terminology, so I'm a bit confused which one refers to what. So our stored vectors become increasingly larger as our original vector dimensionality d increases. Aha. Okay, d is the original dimensionality. This quickly leads to excessive search times. So number of vectors goes to million when the number of bits is d times 2. So does this mean that we have a subvector of dimensionality 2 and here we have 64? And then milliseconds, okay. Which is mirrored by our index memory size as well. So index LSH is not suitable if we have large vector dimensionality. Instead, it is best suited to low dimensionality vectors and small indexes. If we find ourselves with large d values or large indices, we avoid LSH completely instead of focusing on our next index, HNSW. Okay. Let me think for a second. What's n bits exactly? Still confused with the m bits. Resolution of bucketed vectors. So is 4 the resolution or what? Okay. So let's go back to the example here. So the numbers, let me just see what this is. Maybe let's skim through the notebook because they have a bit more quantitative results for this threshold tuning. Okay, so 20, we get some results, and then modify the threshold T, which is the cutoff point on our similarity axis as to where we would like a given cosine to rate as a candidate pair or not. So we compute for different bands. We grab the R value, we have the S scores, thus we compute the P scores. And then we plot that. So a B value of 20 have us a threshold value T slightly too high. So 25, we get that many candidate pairs. Let's see what they do here. Shifting from 20 to 25 has reduced the number of non-candidates around 0.7 to 0.8. What does that mean? And we can see that the number of candidate pairs in total has increased significantly too. Okay. This is a good resource once we start using the fuzzy deduplication. I wonder whether there is any rule of thumb here, or we actually have to just plot stuff for our data and see and optimize the threshold. Let me quickly go through some of these, through some of the code here. Normalize. Plot the cosine. Okay, let's go through this snippet of the code here. Shingles, 1 hot. That's how many samples we've got. And then for the sample size of 50K, we randomly choose X and Y. And we want to see whether this pair is a candidate pair or not, I guess. If that one had been already chosen, or X and Y are the same, then we just skip. Otherwise, we add them. We grab their signatures. If they are in the candidate pairs, then we get 1, otherwise 0. And we also compute the cosine similarity. Okay, that's how we plot these graphs. these charts. Okay, so we have cosine here and the candidates. We can actually tune our LSH function using B, and we have a formalized function that tells us the probability of identifying a pair as candidate pair given their similarity. What's the difference between this one and this one here? I don't see any difference. Cosine norm. Aha. So from here we can attempt to modify the threshold. We get some feeling, and then we do a different band like 25, and we compute that and we plot with cosine and with cosine norm, and then we have the conclusion. So it has reduced the number of non-candidates okay. So what's the conclusion? Why didn't they just say what's better here? Which classifier is better in this example? What's the false positive rate and the false negative for this and this chart, for 25 and for 20? Okay, I get the principle. Makes sense. Let's quickly go now through to our script here, and let me see the constructor. What can we use here as the arguments? Okay, so we can also pass in the threshold. Let me open up this on the side here quickly. Put this here, go here. So we specify the params and the number of permutations. Let's see what else can we do. And by the way, I got these numbers from one of the papers. I'm not sure which one I think it was the Nordic pile or something, the Swedish LLM paper. So threshold, the Jacquard similarity threshold between 0 and 1. The initialized min hash LSH will be optimized for the threshold by minimizing the false positive and false negative. By minimizing. The number of permutation functions. Okay, so this is the size of the vector. And for some reason, these guys use like 9,000. I think their data set was huge. That's why they had to use a very, very, very large, big number here. And then you can also pass in the parameters, number of bands, and size of each band. Threshold and weights will be ignored if this is given. So it seems there are two ways to specify the behavior here. One is to directly put in the band and size of band information and number of permutations, and the other one is to use the threshold and the weights. Okay, hash function. Okay, you can also specify the hash function. Weights must sum to 1, and the format is false positive weight, false negative weight. For example, if minimizing the false negative or maintaining high recall is more important, assign more weight toward false negative. Try to live with a small difference between weights. Okay. So if minimizing the false negatives, so that's on the chart we were looking before. False negatives are basically when we output 0, they are not candidates, but they actually are because they have very high similarity threshold. So basically this is, I think this is allowing us to move that, well, threshold instead of specifying. So then why would one want to use B and R directly? Why not just use this? Would be fun to see what's the, if we specify if we specify number of permutations and threshold, I think we can do it like that as well. We have to think what's, for our use case, what's more important. Okay, examples. Create an index with 128 permutation functions optimized for Jacquard threshold of 0.9. And we end up with B and R being 5 and 25. Well, if this is the case, then this is not 128, right? The built-in optimizer will try to minimize the weighted sum of probabilities of false positive and false negative. The algorithm is a simple grid search over the space of possible parameters. Note that it is possible to get B and R that do not sum to the number of permutations, as we've just seen above, leading to unused permutation values in the index min hash. Hey Sergey, welcome man. Yeah, it was a very fun trip, but like I'm not traveling over the next period. I don't wanna, having these breaks when I'm working on a project is, context switching is not something that is good. So I'm just gonna be relentlessly focused on the project until the end of the year at least. And as for Ramsey's question, that's a very subjective question, although I think most people would agree that PyTorch is better. Depends what you want to do. This is because the optimizer only considers bands of the same size, and the number of bands is not necessarily a divisor. Okay. Instead of using the built-in, you can customize the LSH parameters yourself. The snippet below creates an index with 128, 16 bands, each of size 8, skipping the optimization step. Okay, this is basically how I understood it as well. Create an index backed by Redis storage. Okay. Well, let's see. 9,000. Let me quickly find the paper where they've used this. Literature, positive duplication. I think it was refined web paper for the Falcon NLLB model. Let me load it. Let's see the settings they've used. Okay, let me see, where did they specify the arguments for the fuzzy duplication. Okay, they say here we perform min-hash duplication using 9,000 hashes per document, calculated over 5 grams and divided into 20 buckets, each having 450 hashes. We found that using less aggressive settings, such as the 10 hashes of the pile, resulted in lower dedup rates and worsened model performance. Okay, that's going to be super intensive to calculate something like this. But they say documents, so that probably means they have much less data points compared to what we would do, because we have our data point is a sentence in our parallel corpus. Let's quickly see what the pile paper has done. So let's open it up quickly. Whoops. Let's just quickly open up the paper. Find the fuzzy settings. They also use the data sketch library, apparently. Or let me just see. No, this is actually just explanation of how the components were computed. So to produce a dataset, URLs and their associated metadata were first extracted from all Reddit submissions. URLs were deduplicated. Okay. Due to the memory constraints, we did not perform pile-wide duplication at the document level. The same technique was used for both Open Web and Common Crawl, min hash with the Python data sketch library. We use 10 hash functions for each min hash and an approximate Jacquard similarity of 0.5. Okay, so basically they specify the threshold and number of permutations equals 10. The main challenge here was computational, leading us on a journey through the various LSH persistence options. A simple quadratic min hash comparison of all documents would have taken several 100,000 years. We do not have sufficient RAM for in-memory LSH, and then they use the Cassandra backend. Okay. I think for HBS, for the data I care about at the moment, we can just do everything in memory. So that means that's less of a concern. Let me just ping. Let me just ping like Chris and ask him what he thinks about the settings. Why is this? Why do these guys use like 10 and refined web uses 9,000? So Lutheria used 10 here. Jacquard similarity 0.5. These guys use 9,000. I guess I'm not sure about the size of the data sets. Let's kind of skim through the paper here just to see the requirements they had. 100 to 250 AWS C518 large instances, and each of them has 72 virtual CPUs. So that's a ton of compute. 10 to 20,000 vCPUs. That's, given how big the number of permutations they are using, this is to be expected, I guess. Let me quickly skim through these 2 pages here. We make use of the 2 deduplication methods, exact substring and near dedup. Okay, more information in the appendix. They start with the most scalable one. and document pairs with a high n-gram overlap are identified. How do we specify? Okay, we specified the n-grams before in the processing, before we even called the LSH. Okay, let me just quickly go through this. Min hash approximate matching allows us to identify templated pages or otherwise very similar content. Signing. Normalize the content to increase the recall. Punctuation is removed. Text is lowercase. NFD Unicode normalization is applied. Accents are removed and all white space is normalized. We tokenize the resulting text using the GPT-2 tokenizer and obtain the set of unique n-grams for each document. Hash functions are used to obtain a signature. For each hash function, the smallest value is kept from hashing every unique n-gram in the document. The ratio of matching hashes approximates the Jacquard similarity of the sets of their unique n-grams. Okay, basically that means we classify those sentences as candidates when they have a big overlap of n-grams as defined by us. The n is defined by us, obviously, in the pre-processing stage, and the threshold as well. The normalization part is important though. That's something we want to do. And then matching. Okay, this is again, we've seen this before, the same equation. For two documents I and J whose ratio of matching hashes between their min hash signatures is this. Okay. They use the same parameters as Lee et al. And the probability that a document pair with a similarity 0.75 or 0.8 will be marked as duplicates will be this and this. Diminishing rapidly for smaller similarity values. What's this paper? The duplication training data makes language models better. Back to where we stopped. Google Brain Team. Paper from 2021. Okay. And then they mentioned the exact substring deduplication, which we already have implemented. Maybe we can have the same curve just with a smaller number of hashes. We compute 9,000 and okay, let's grab these numbers here. We just keep that somewhere in here. We're done with that. They use 9K permutations, whereas we can use a smaller number. Let's quickly see what's going on here. Okay, we don't need this. This is more relevant when you're building like a large language model dataset and not a parallel corpus. So exact substring concatenates all the documents in the dataset to create a single long text sequence. Then it builds a suffix array in linear time, an array of the indexes to a lexicographical ordering of all the suffixes in the sequence. Finally, duplicate sequences can also be found in linear time using the suffix array by simply traversing the ordered list of suffixes and comparing the beginning of each pair of two consecutive suffixes. We apply the same normalization and documentation as for min hash to the content of the documents before concatenating them. Okay, I think that's everything we needed. Yeah, I think we can just use, because I mean, for the pile they use data sketch, I think it will be good enough for us as well. Okay, let's go. Let's start going through our data set. HBS data, let's start processing it. and when I say processing, I mean filtering, and everything else that we've seen previously, meaning binarization, sharding, and everything else. Okay, so for the first iteration, I'm gonna go with English to HBS. So that from English to Croatian, Bosnian, and Serbian. And then I'm gonna skip training a dedicated HBS tokenizer. We're gonna just reuse the SPM 200. And we're gonna also skip, we will not be using a custom LID. We can just reuse some of the existing LID models. We will not be using any additional data other than Makoku and Opus. And that's it. That's going to be the first iteration. The second one, I'm going to do the same thing. So English to HBS, but I'm going to try and train, make it a bit better by having a better tokenizer, and all of the other things here. Okay. Let's start. What's the first thing we want to do? These are some optional things I was planning to potentially do. We might want to filter out dates and number of sentences from mine datasets, because these are always bad. Just because of the way how the mine datasets are formed. We might want to change the length ratio during the filtering stage. That's one more thing we have to keep in mind. So again, this is just some filtering details. Line length analysis. Okay, this was the task I left for anybody to pick up. Let me see what other people were picking it up. I think Smith mentioned he might take that one. We go to issues. Good first issue. Smith wanted to take this one, but nobody took it. The idea was to find why we have these spikes in the histogram. Why are these so regularly spaced out and then they are dampened as we go to the tail of the distribution here of the histogram? That might point us to some issues with the data. Then the second question is 1050 characters in HBS. What does that map to if we tokenize using the SPM 200? Remove punctuation from both ends of the sentences. I think this is also done. Filtering. And then add data for script tag when using Cyrillic versus Latin scripts. Let me think, what do we want to do here? This might require us to have, again, a custom trained tokenizer, because the set of languages that's in the SPM 200, this will not be supported. So like we only currently have, I think, Serbian Latin inside of something like this, inside of an SPM, but we also want to have something like Serbian Cyrillic as well. Hey Hugh, thanks man. Glad to see you here in the stream as well. We'll probably take a day or two just to get back into the old rhythm. And add the data source label. How do we do that exactly? We're gonna see all of these questions being answered over the next couple of days. Again, filtering. And this one as well. And fuzzy duplication as well. Okay, if I recall correctly, we have around 95 to 100 million sentences for each of the HBS languages. We definitely want to reduce that and make it much higher quality. Just think. How can we add this? This simply will not be supported for Serbian Cyrillic with SPM. I think we'll have to leave this for later. That means we might have to just ditch all the Cyrillic data and just use the Latin data. Okay, just a second, guys. Okay. Let's move this here. So this is all the filtering that we'll be doing for the first pass. Before we go there, I'd love to understand these spikes to avoid any unforeseen issues down the line. A second. Super hot in Belgrade, still end of September. Have to turn on my AC. Okay. Let's go to data. Analyze the data. And let me see quickly. We want to see the line lengths. For certain languages, like Serbian, for example, or something. This is all the data we have. I've prepared all the data in the previous streams. Now I just want to analyze it and quickly understand why are we getting the spikes. So let's start with like Serbian. Let me see quickly. Let's go to long JSON. Analyze data. Serbian is already set as the path here. We have the length vectors being set there. So we're good there. Let's just set the right config here. Analyze the data. And let's kick this off. Will this be enough? Just line lengths? I think it will. So analyze primary data. It would be cool to see where those spikes lie. So we can maybe pick out one of these spikes and just see what are the sentences. I think this is probably just because of the duplicates. We might just have a ton of duplicates. And after the duplication, maybe we will not be seeing these spikes. I think that makes sense. Okay, let's run this. We are computing the line lengths. And at the end, let me just put a breakpoint somewhere here. Dedup number of send line lengths is here, so I'm gonna enter there and just analyze the spikes and see where they lie. And then we're gonna try and modify the script so as to pick out only those. We can maybe filter out only those sentences that have that particular length. And then I can analyze those to see what's going on. That's the idea. So let's first visualize it. Let's find the points on the x-axis where we get the spikes. And then let's filter out subsets of data that have those lengths. And then we can see what's the thing, what's going on there. Okay. Let's go. So this is for English. Let's print this. Here it is. And then for Serbian, let me just close this. Let's get back to here. Okay. It's the same thing here. Okay, now how do I get the spikes? This is not an interactive plot, so I can't really see it. Do you guys have any tips? What package should I be using to get in some interactivity here, and so I can pick out the exact values? Matplotlib is really rudimentary. Maybe Seaborn or something supports it. Let me quickly see that. I mean, I could always do some gradient analysis or something to find the spikes, but that's a bit too much. Let me see, Seaborn interactive plot, or even Matplotlib, maybe Matplotlib interactive plot. Let's quickly see this. So yeah, this is what I'm looking for, plus the option to, can I zoom in with the current plot here? Can I actually zoom in? I can't even zoom in, or maybe I can if I click this. And then if we focus on one particular element, okay, we can actually do it like this. Let me zoom in additionally. Okay, so the value seems to be at 140. 140, 141. Why is this not perfectly aligned? Maybe because because this is a, wait, this is histogram, so my bins might not be perfect. Yeah, this is messing up the exact value. I want to get the exact length at which we, okay, let me think for a second. Compute the line length. Maybe we should multiply with length vector here. We just need to append the line length directly. So I'm gonna comment out this temporarily. And then, what is this wizardry? We're just trying to do some analysis and understand why we get certain spikes in the histogram for the line lengths of the data points for Serbian corpus, if that makes any sense. It does require some context to understand, so stick around if you're curious. So compute the line lengths, and then let me see, ideally I would want to have on the x-axis, this is Python. Let me think step by step. Bin centers, histogram, bin edges. This is Ubuntu. How can I get the number of outlier line lengths? We grab the histograms. Okay, let's see what's the size of this one. What's the max element? Use Arch Linux. I use Ubuntu. Okay, 5 and 1049. Why is this already perfectly inside of these boundaries? Because, okay, we filter out the ones that are above or below that threshold. Let me think. Well, let's put exactly 1000. Let me think for a second. If we put 1050, will this make any sense? Let's try this. I'm gonna kick off the run again. Now we don't have the normalization with the length factor, and we will be using the same number of bins as what's the max number of characters. I didn't modify Ubuntu other than what I just needed to get this project running. Just bare basics and the tools I need to run this code. Okay, let's see what we'll get here now after removing the normalization with the length. Okay, here we are. Will this make any sense? Okay. Much smoother now. Yes, so the brief explanation is what you're seeing here is across the whole corpus of Serbian text, English to Serbian. You can see how each of the sentences, so we have the line lengths on the x-axis and number of sentences with that line length on the y-axis. So we just had a histogram here, and it's fairly continuous because we have a lot of data, except for the dip here for some reason. But I wouldn't be too obsessed with this dip. This is probably just, let me see, it goes to 0 right at 155. Why would we just miss that particular? Interesting. Where does this whole thing start? Let me just take the loop again. Zoom in here. So we start at 6. Oops. Let me just try this again. And again. So 650 is where, so 650 is the first one. That means we're shifted by 0.5 because I filtered all of the ones that have 5 characters or less. So that means the first one is 6.5. And 6.5 is basically just 6 characters. So that means that this particular dip here happens at 154. Okay, let's see the Serbian. So it looks like this might have been just side effect, just a side effect of using a particular binning number of bins for histograms. So those spikes disappeared now that we have smooth. Now that we have like a single bin for every single number of characters. Let me see whether this is in this roughly same. So for some reason this is 0 again here. This is weird. Okay. Yeah, I think we're good with this task. It seems that when we number of bins. Hello. Change the world. What are you guys trolling? Well, I eat Borania and Lebanon. Nice. Nice. Welcome to the stream. Okay, let me see here. Let me just close this issue because there is apparently there is no issues here. The reason we had this spikes is because apparently for some reason text seems to cluster so that we have more data for certain sub ranges here than for others. That's still weird, but like I had 500 bins before this. Now we have 1050. This still probably means that we have some duplicates happening at these particular lengths. Okay. The chart above was just a side effect of using a coarse number of bins for the histogram. It's still not super clear why we have why do we have 153 and 154 lengths and then 55 and 6 are not that prevalent. Okay, let's now go back to 500 again. Let me just rerun this quickly. Okay. Waiting for this to compute. And let's see whether we still have the spikes. I mean, we'll certainly have them. I just want to see where they occur. It doesn't make any sense still. Why would we have such patterns? So why do we have these patterns? Why is it so that interesting. Let's zoom in on this one. So 100, 300, 204. Let me just see what we have here. The first one is again at 7. Why is this one at 7? And here we end up with 48. Around 102, 103 we have clustering going on. 103 we have a clustering. Let's see why is that so special? Why is 103 so special of a number? Ideally we would be able to just extract that data only. Let me think. Let's do that. Let's do something like this. Compute the line lengths. I'm gonna quickly modify this code to if length 1 is like between 102 and 104. Then enter here. And just return those lines back so we can quickly analyze them. I'm just gonna append these here. So extend and do the same thing here. And now that we have these, at the end, I'm just gonna dump them somewhere. Maybe first print what's the length of those, and then then basically something like this. So we open it up and we just save them. Yeah, this should work. Let's see what happens if we rerun this. Or maybe, sorry, we just actually have to, let's focus on the Serbian. Okay, waiting until we collect all of those lines. Let's see how many we've aggregated already. We're processing open subtitles, which is a bit longer data set, so that's why we're waiting here. Okay, there is gonna be a ton of lines here. Okay, still not too much. Hopefully we see some pattern here. Let's see, let's just dump this. Whoops. Okay, and let me open up that file. Okay, as you can see here, we picked out sentences that have particular line length. For some reason, we have a mix between Serbian and English, which is not something I expected to see. Didn't we pick out only... Wait, something is weird. I might have... I might have commented out... No, let me just rerun this. I think we had wrong code the last time I was running it. I didn't comment out this on time. The program was already running. So we were computing, let's do it like this, temporary lines, and then extend. So this would only pick up Serbian. And then let's just make sure again that 103 is the right. And then we can analyze this text using like fuzzy deduplication or something, just to see how many of them are similar. Or exact deduplication as well. Let's do that. Kick it off again. And wait until we hit this line here. let's see this, and then in the next stream we're going to analyze the data using fuzzy dedup and exact dedup and see whether there is any significant number of duplicates, and that's the reason maybe why we're having these spikes. Yeah, I'm always open. Feel free to shoot me a DM. Okay, open subtitles. Again, this is one of the longest data sets. That's why it always takes a bit longer. And here we are. Let's go. Okay, this is English. Let me just open up this spike. Again, it's 103. Okay. And for Serbian, let me hit F5 here. Will it be the same thing? Or do I need to modify for Serbian? So here is a spike here. I think it's also 103. Yes. Sounds good. Let me now see the output. This should now be all Serbian text. But it's not, which is weird. Let's analyze this in the second stream. So up for a small break. This is the first time. This is the first stream after China trip. So I'm still getting used to just sitting down and working my ass off. And it's lunchtime as well. So let's catch up after the break in like 30-40 minutes. I'll let you know on the Discord channel. Keep an eye out for open NLLB channel if you're curious about this project. Under the pinned messages, you'll find all of the information that might be interesting to you if you want to learn a bit more about the project. And that's it, guys. Catch you a bit later. Cheers, guys.